The silent gray desert stretches endlessly beneath a black sky, filled with immovable stars. Wheels crush powdery regolith as the first generation of lunar mining crawlers rumble across the surface of the moon, carving tracks into untouched terrain. Their mission is urgent and monumental: to extract water ice hidden in permanently shadowed craters, and to scoop up trillions of tons of dusty rock, known as regolith. Stripes of headlights disappear over crater rims as machines dig, melt, drill, convey, and store. Each bucket of soil brings humanity one step closer to staying permanently off Earth. Robotic prospectors pepper the landscape with seismic hammers and neutron detectors mapping hidden pockets of ice near the poles. Ice once ignored, now valuable as liquid water to drink, oxygen to breathe, and hydrogen to burn. Tethers and conveyor belts stretch between ice pits and smelting plants. Sunlight glints off mirrored concentrators positioned along crater lips, bouncing intense beams into the permanent darkness to heat extraction rigs buried in sub-zero shadows. Ice cores are drilled, lifted, and fed into giant ovens. There, the ice sublimates into vapor, funneled through chilled coils, to condense into liquid water stored in silver bladders. Elsewhere, regolith is dumped into microwave furnaces where temperatures soar. Raw dust is transformed into beads of molten glass and metal. Iron, aluminum, titanium, and silicon are separated through electrolysis and slagging. Oxygen is pulled from oxides vented and stored into pressurized tanks, holding breathable life. Lunar soil, once a symbol of desolation, becomes a warehouse of elements. Dozens of nations and private companies dispatch autonomous fleets in fierce competition. Each aims to dominate resource-rich craters and ridges. The South Pole becomes a prized hunting ground. Sun-facing highlands offer near-constant sunlight for power, while adjacent craters harbor billion-year-old ice. Disputes erupt silently between rovers as artificial intelligence algorithms calculate rivals' intended claims. Machine arms whip faster. Code wars ripple through communication relays as they scramble for rights to ice veins and rare metal ore. The once empty tranquility becomes a battlefield fought not with bombs, but with patents, protocols, and programming. On the near side, factory modules inflate like silver balloons. They transform into mining hubs, littered with three-dimensional printers, chemical reactors, and dust-covered solar farms. Enormous thermal batteries burrow into the regolith to store sunlight as heat during the frigid 14-day lunar night. Here, molten regolith flows like lava inside electromagnetic crucibles. It forges thick bricks, pipes, and structural trusses. Wafer-thin solar panels are printed directly from lunar silicon. They are glued onto frames using sintered glass paste. Slender towers start to rise not to reach the stars, but to harvest the endless sunlight beaming overhead. Human crews remain in orbit, inside radiation-shielded habitats, watching as their mechanical pioneers toil below. They review mineral assays. They send commands through laser links. They test DNA-thick biofilms to eat lunar dust and release oxygen. Bold engineers plan to carve underground ice caverns into fuel depots. Water will be split into oxygen and hydrogen for future rocket ambitions. Hydroponic experiments grow lettuce under LED arrays, fueled by lunar-made power cells. In makeshift labs, dirt is mixed with epoxy binders. It produces prototypes of simple circuit boards and pressure vessels. Every experiment marks a step toward a closed-loop economy. In space, the terrain is harsh. Jagged rocks slice carbon polymer skins. Lunar regolith, sharper than glass shards, infiltrates servos and joints, destroying bearings and scraping gears. Electrostatic dust clings to solar panels, reducing energy yields. Engineers deploy dust wiper robots and emitters that pulse electric shocks, pushing dust away from delicate hardware. Nighttime temperatures crash to deathly lows, freezing hydraulic lines solid. Daytime heat roasts electronics. But every time a component fails, it is melted, printed, and reborn in nearby fabrication modules. Moon mining adopts a philosophy of self-cannibalization. Nothing dies permanently, only recycled. Soon, mobile water haulers shaped like armored pillbugs crawl between ice pits and fuel stations. They pump melted ice into blister-white tanks. These tanks feed into chemical processors, turning harvested ice into rocket propellant. Supercooled cryofactories hiss clouds of vapor into the vacuum. They condense oxygen-hydrogen fuels in ready anticipation of outbound lunar launches. Near equatorial sites, bulldozers flatten gray dust into hardened pads, where experimental launch platforms begin to materialize from regolith-printed cement. They are early testbeds for a vision of low-gravity industrial spaceports. Above them, steel claws grasp regolith to build blast walls and berms, shielding nearby equipment from rocket plume erosion. Meanwhile, deeper beneath the surface, experimental boreholes tunnel about 2.8 miles down through basalt layers to probe for lava tube networks. These are natural empty caverns carved by ancient volcanic rivers. If located, these tubes promise shelter from radiation, micrometeorites, and temperature extremes. Rovers fire radar pulses and seismic shots into the crust, mapping possible chambers. Test charges blast open entrances, revealing yawning lava tubes stretching for dozens of miles. Lantern drones drop inside, scanning walls. Engineers plan to seal entrances with regolith bricks, then pressurize interiors and convert them into natural bases. Some lava tubes reveal unexpected veins of ilmenite and anorthite source materials for extracting iron and aluminum. High above, relay satellites form a glittering constellation in polar orbit. They bounce signals between miners, Earth, and future construction projects. Solar-powered communication drones flutter like dragonflies across crater rims, relaying telemetry and thermal scans. Others carry spectrometers, hunting for minuscule traces of platinum group metals, helium-3, and rare earth elements. Companies hope to one day export these luxury materials to Earth. But for now, the focus is simple: logistical survival, autonomy, and proof. And that the moon can feed its own machines. By the third cycle of excavation, swollen depots contain thousands of tons of water and brick-like stacks of processed metal ingots. Alloy mixing stations transform iron and titanium into ultra-strong steel panels directly on the lunar surface. These panels are slowly laid to form the first prototype shelters. Gigantic scaffolds rise in angular arcs. Robotic welders stitch trusses into dome skeletons. During construction, mobile regolith buckets pour gray dust over the structures, burying them about 46 feet deep within lunar soil walls to protect eventual human occupation. Inside these newly fabricated vaults, machines melt ice in coils, releasing water vapor that condenses on chilled metal to settle dusty interiors. Life support experiments begin flushing oxygen into test volumes. The goal: create airtight, self-pressurizing habitats. Made entirely from lunar matter, teams of artificial intelligence-driven architects optimize new printing algorithms. They program swarms of spider-like bots to weave carbon polymer tendrils into strong tensile frames. They instruct bulldozer-sized printers to layer self-fusing ceramic. These next-generation miners become builders. Their activities accelerate exponentially. The moon's barren face sprouts clusters of metallic, glassy structures. Some frame future living quarters. Others become chemical refineries, furnace rooms, recycling depots, or darkened hydroponic trenches. A transportation spine emerges. Long magnetic tracks where cargo sleds zip between sites, bearing regolith, metal ore, and water tanks. Above them, sunlight glimmers off superconducting power cables, connecting crater-rim solar plants to deep-pit mining operations. Remote biologists inject hardy lichens and cyanobacteria into sealed pilot chambers built beneath the surface. These organisms feed off crushed lunar rock and recycled waste to produce breathable oxygen and organic biomass. Half-buried greenhouses hum with chillers, heaters, and LED strips. Lettuce leaves slowly unfurl their emerald edges. Beneath pinkish grow lights, ice-fed drip systems water rows of microgreens. Each leaf grown on the moon becomes a symbol, a living flag, staking humanity's permanent claim. Over time, experiments advance toward soil creation, mixing powdered regolith with composted algae, microbes, and pulverized rock to simulate Earth-like loam. Moon dust is slowly being tamed. Logistics change drastically. Supply missions from Earth are reserved for electronics, seeds, artificial intelligence processors, spare nuclear battery cores, and medkits. Everything else is built locally. Regolith foundries produce thousands of strong bricks per day. Metal extruders shape beams and panels. Isotopic separators begin extracting helium-3, a potential future fusion fuel. Companies silently map claims across the lunar surface, preparing legal arguments under Earth-based space treaties. And silently beneath them, early legal wrangling begins for future sovereignty, taxes, and export tariffs over lunar resources, even as diggers tear into rock. Lawyers on Earth draw boundary lines across maps no human has yet physically stood upon. To maintain momentum, fresh-generation autonomous bots are delivered directly from Earth orbit. These arrive as flat-packed kits landing via reusable landers. On landing, they automatically unfold, connect cables, and join the mining swarm. Some older machines are now obsolete but not discarded. Instead, they are melted down in mobile factory units to produce spare parts for newer models. Everything on the lunar surface is consumed or transformed. Not a gram of precious material is wasted. Amid this organized chaos, a small group of human supervisors finally descend, encased in protective suits. They stand on regolith-shrouded platforms, overlooking an ever-expanding plain of machines. They are the first to witness that the moon is no longer dead rock, it is becoming a living industrial organism. They walk carefully between crater-edge solar farms and drilling rigs that vanish into perpetual darkness. Inside pressurized walkways, experiments brew fuels, plastics, and metals in pure silence. Each step stirs dust into clouds, only to let it slowly fall back down under lunar gravity. Cameras capture every moment. These images beamed back to Earth inspire a new generation of students who no longer see the moon as distant, but as the next frontier of civilization. Robotics teams test underground transport pods floating on magnetic pads through tubular tunnels carved from lunar basalt. These pods protect sensitive cargo from radiation and meteorites. They also become prototypes for eventual human transport tubes, blood vessels, FT-mote, of a future subsurface civilization. Within warehouse domes, giant printers produce tubes and connectors like insect chitin. Out on the plains, titanic bulldozer spiders reshape the terrain into flat plateaus for new facilities. Industrial expansion becomes addictive. The more the moon provides, the more humans demand. The more they build, the more needs arise. More power, more water, more metals. Eventually, new types of fuel refineries appear near ice pits. They fuse lunar hydrogen with imported nitrogen to make ammonia-based thrusters for surface vehicles. Designers dream of transforming lunar dust into fibers strong enough to weave future space elevators. On screens inside Earth-based mission control, rapid reports pour in from lunar sensors. Radiation levels, dust storms, ice purity, ore concentrations, oxygen production rates, bacterial growth curves. Everything is tracked. On the little balloon, in real time, the moon is no longer separate from Earth, but a tightly connected industrial partner. Within 5 harvest cycles, the mining operations feed enough material into construction pipelines that blueprints emerge for massive habitat domes, radiation vaults, and pressure-sealed tunnels. Teams propose to build long-term living quarters, biological labs, and hospitals entirely from regolith-derived glass and metal. Engineers experiment with lunar bricks doped with polymer resins to withstand impacts from micrometeorites. Others design underground microgrid reactors powered by lunar thorium and uranium ore, scavenged in small quantities from regolith, with surplus oxygen, hydrogen, and metals produced on site. Human presence becomes not just possible, but economical. The entire operation becomes a dry run, a dress rehearsal, for all future human habitation. Beyond Earth, every challenge encountered on the Moon has a lesson for Mars, the asteroids, and beyond. If humanity can master mining, manufacturing, and survival on the Moon, without constant lifelines from Earth, it will have built the first ever extraterritorial ecosystem, a system that feeds itself, powers itself, heals itself, and expands itself. At long last, the once barren lunar surface is no longer an alien wasteland. It is a frontier under transformation. The regolith itself breathes, sweats, and gives birth to machines. And soon, it will support thriving human outposts. For the first time in history, humans have proven that life can dig deep into another world and begin to grow.